All right, so let's get started. So today we're gonna. It's basically gonna be a new topic every day. You may or may not know how these things are working, but today is exponential and logarithmic functions. On Wednesday, it's going to be matrices. On Friday, it's going to be probability theory, and then a week from today, it's going to be information theory. And although it's a different topic every day, you will see stuff used in previous lectures. You'll see them in future lectures. So, for example, in information theory, it's going to use stuff that you've learned the previous 3 lectures. So it's going to use logarithmic functions, and it's going to use matrices, and it's going to use probability. You get to information theory. Then, after information theory, there's sort of a clean break, and we do trig, which leads us up to waves, so wave theory. And then there are some miscellaneous topics after that, including queuing theory, number theory, graph theory, and I think that does it. So there are 11 topics in all. You have the textbook. Every day's lecture covers 1 chapter. So it's just chapter a day, and the chapters go through in the same order that they're going to go through here. So chapter 1 today, exp and log functions. Good. Any questions on that? All right. Let me tell you a little bit about myself. My bachelor's degree is in physics. I started out in math, but at the time, I liked physics better. I actually had a very great, charismatic physics professor who kind of just made me decide to switch to physics. Well, I got my bachelor's degree in physics. I then got a master's and a PhD in computer science. But it was very much on the theoretical end of computer science. So there was a lot of math involved. So algorithms, complexity of algorithms, complexity of problems, things like that. So I've kind of come full circle. So things I'm not particularly strong in, I will tell you right now, are electrical engineering. Some of the other engineering topics I don't have a degree in. I've learned a lot about them outside of school, but my strong things are math, which is why I'm here, and physics, and some engineering. I know a little bit, and certainly computer science. So, all right. Any questions before I go about anything? All right, so let's dive right in. So today is exponential functions. We'll talk about exponential and logarithmic functions. We'll show some graphs. MATLAB and Microsoft Excel are 2 software tools which are useful in understanding these things if you know them. Other tools include Maple, Mathematica, which are privately distributed and expensive if you're not on a group license. There's also Sage, which is a free open source mathematical package that does these things. I tend not to use any of these. I am sort of old school. I do things with pencil and paper for the most part. I do calculations, and I've done a lot of programming, but not in the service of what we're going to be talking about. So I tend to be old school. So doing things this way are optional. I have used these tools a lot in the past, but I tend to prefer doing things, teaching the old-fashioned way. So I won't be asking for you to do a lot of computer analysis or computer graphing or anything like that. Okay. That you will certainly do in other modules, but not so much in this one. This is really sort of brain, pencil, and paper, or pen, if you prefer. All right. So, and then the capstone of today is talking about decibels and signal levels, which are on a logarithmic scale, which is why we have to learn log functions before we get there. All right. So, to learn exponential and log functions, we have to talk a little bit about functions. So some of this is covered in chapter 0. A function is just some arbitrary association that associates some object in one set with some object in another set, maybe the same set. We think of an association as a pair of things, an input object and a corresponding output object. The set of input objects is called the domain of the function. So the set of possible inputs to the function is called its domain. And if f is a function, we write dom f. We call this the domain of f. So if x, some object x, is in the domain of a function f, and y is the object that f associates with x. So x is in the domain, so f associates some output y to the input x. We'll denote that output by f of x. Now, when I say input and output, you might be thinking computers, okay, I input something to a computer program and I get an output. This is actually much more basic than that. This f is completely arbitrary. It doesn't have to be computable in any sense. It doesn't have to correspond to an actual machine that turns inputs into outputs. It's just some kind of bare association, associating an input with an output. Okay, so we also say that f is defined at input x. All this means is that x is in the domain of f. So the domain of f is the set of all inputs for which the function has a well-defined output. Okay. Sometimes we'll actually specify the domain explicitly. And we will say, that this point is in the domain and that point is not in the domain. We'll be very clear about what is and what is not in the domain. Even though that might go against our intuition, sometimes that's necessary. All right. So here is how we might picture this in a little Venn diagram. Here is the domain of f. It's a set. This circle, the shaded circle, and a point x in the set in the domain. And f associates this output y equals f of x. In another set, which we call the range of f, or RNG of f. This is the set of all outputs of f. This is the set of all points that are outputs corresponding to inputs in the domain. Okay, so we call that the range. We say that f maps the point x to the point y, so that terminology is also used. We also say that f maps the domain into the range. So we use the word mapping. So a function is also called a mapping or an association. Okay. So here's an example. So one way of specifying a function is to give some expression that takes some variable, letter like x, and some expression involving x. And the idea is, if x is an object in the domain, you can plug that value into the expression, and the value of the entire expression then gives you the output. So, for example, the square root function is defined like this. On some arbitrary point x in the domain, f, the function f, is associating x with its square root. So, in this case, what do you think the domain is going to be? Positive integer, okay. Could be positive. Could be more than just positive integers. It could be just positive reals, okay. How about 0? Sure. Yeah. What's the square root of 0? 0. All right. So let's include 0 in the domain. So I'm going to make a very, very firm distinction between positive, which means greater than 0, strictly greater than 0. That does not include 0. 0 is not positive. Negative, which is strictly less than 0. 0 is not negative. 0 is neither positive nor negative. So the entire real line is chopped up into 3 pieces. The positive reals that are greater than 0, 0 itself, and then the negative reals, which are all less than 0. And so, as we surmise, well, maybe the domain should be the positive reals with 0 included. And if you really want to be, this is kind of clunky, but some people say the non-negative reals. So all the reals that are not negative, which means 0 and the positive. Okay. All right. So here I'm defining an expression f. I'm defining this function f by an expression that says what f maps every point in the domain to. It maps it to its square root. By default, if I don't specify the domain, if we don't specify the domain is just the set of all possible values of x for which the expression makes sense. So if we're restricting ourselves to the real numbers, which we will for a while, this makes sense for all non-negative reals. So the domain consists of 0, all the positive, but it does not consist of negative numbers. Okay. So in this case, the domain of f is, reading it this way, this is the set of all x such that x is greater than or equal to 0. Okay, so let's look at this notation. Let me pull this notation apart for a second in case you haven't seen it in a while. The braces mean this is a set of things. And inside the braces, I have some rule, and you can read it off in English like this. It's the set of all values x such that, the colon means such that x is greater than or equal to 0. Okay. Sometimes they use a vertical bar instead of a colon. It means the same thing. Okay. So this is the set of all values x which are greater than or equal to 0. A more compact notation is the interval notation. This is the interval of all real numbers from 0 to infinity. So positive infinity means 0, and then all the positive numbers unbounded. There's no limit. Okay, so we just take all the positive numbers. Infinity here is not a real number. It's not a number. What this means is just 0 and all the positive numbers as well. Okay. I'll explain the square brackets and the parentheses as we go. Does anyone recall maybe from chapter 0 what that notation means? So what does the bracket mean? Yeah, good. So the bracket means you include the endpoint. So the endpoint, the lower endpoint is 0. You include that. If I had a parenthesis here, what would that mean? Right, you do not include the endpoint. And that seems like a trivial distinction, but it's one that we're gonna it has to be distinguished. So if that should be a bracket and you put a parenthesis, that's a point off at least. Okay. So that's not correct. All right, and if I have an infinity here, you always use a parenthesis because infinity is not a number, so you never include it. So, all right, more on that later as the slide says. Okay, so function is some association that maps inputs to outputs. What can we do with functions? Well, the basic operation you can do with the two functions is compose them together. To compose two functions, if I have two functions f and g, the composition of the functions, denoted by this little circle here is, think of this as a binary operation on functions. It takes two functions and gives you another function. So this function, f composed with g, is defined as follows. On any value x, first you apply g to x to get the output of g. And then you take that output of g and feed it to f as an input. So the output of g becomes the input to f. And then the output of that is then the output of the composition. So this is just an expression that says, okay, on any x, we're feeding x into g. So I'm thinking like the meat grinder analogy to a function. If it's feeding x into the meat grinder, out pops some other value, which you then feed into the second meat grinder, which is f. Okay, and then whatever comes out of that, that's the output. So this is a basic operation on functions. So given two functions, f and g, this gives you a third function called their composition. So, for example, f, if f has this domain over here, and that's the range, then a point in the domain might be an output of g. Okay. And then what you do is you just take g of x and map it to f of g of x. So now the question is, what is the domain of a composition? If I know the domain of f and I know the domain of g, what is the domain of the composition? Well, we want the domain to be all the x, such that this whole expression makes sense. So what's a bare minimum? What does x have to, what can you tell me about x, just as a bare minimum, first of all? It has to be in the domain of g, right? Because you're applying g to x. So we think of applying a function to an input is what gets you the output. So we apply g to x. So x definitely has to be in the domain of g, but that's not sufficient. What else has to happen?
G of x has to be in the domain of f.
Yeah, so then we're taking g of x and feeding it to f. So g of x has to be in the domain of f. Those two conditions together are in fact sufficient. They're necessary and sufficient. So there are two conditions here. X has to be in the domain of g. So x has to be in the domain of g, but then g of x has to be in the domain of f as well. So let's look at some cases where the one or both conditions may be violated. So if I have some other point in the domain of g, x1 is in the domain of g, but g maps x1 to some output. Oops, sorry, I'm getting ahead of myself. That maps some output which is in the range of g, because it's the output of g. But that range of g is not inside the domain of f. So we can't allow x1 to be in the domain of the composition because it violates one of those two conditions. It's got to satisfy both. All right. So let's do an example. So f of x is the square root of x. So f here is the square root function. And g of x is the function which takes its input, doubles it, and adds 1. Okay, so g, what it does to x is it multiplies it by 2 and then adds 1. So whatever value you feed to g, that's what comes out the other end. So let's apply the composition of f composed with g to -3. Let's try this. Is this going to work or not? Well, what do we do first? We take -3, feed it to g, stuff it into g, and what do we get? So to do this properly, what you do is you take, well, x represents the input. So here, the input in this case is -3. So you substitute -3 in for x, find the value of the expression. 2 times -3 is -6. Add 1, you get -5. That -5 you then feed to f. And so, but what does f do with its value?
Takes the square root.
Takes the square root. Okay, so now just restricting ourselves to the real numbers. We'll get to complex numbers later. Restricting ourselves to the real numbers. Is this well defined? No. Okay. So even though -3 is in the domain of g, g of -3 is not in the domain of f. So -3 is like this example here, where I have a point in the domain of g, but G at that point is not in the domain of F. Okay. So it's undefined. You got to have both. What is the domain? By default, all the x for which this expression makes sense. Yeah, just right. All real numbers. So this makes sense for all real numbers. There are no restrictions at all. So the domain of G, we can write the real numbers this way. It's the entire interval from minus infinity to plus infinity, not including the infinities. Okay, so this is just another name for the set of real numbers. So everything's in the domain of G. So again, the domain of F we decided was that. And the point is, even though negative 3 is in the domain of G, G of negative 3 is negative 5. And that's not in the domain of F. So if we test both conditions explicitly, we see that x, yes, is in the domain of G. In fact, that's always going to be true. And 2x plus 1 has to be in the domain of F. In other words, if you want to solve for x, okay, so if 2x plus 1 is in here, that means 2x plus 1 is greater than or equal to 0. So if I write the equation, I'll do it on the slide because they want me to do that. Oops. All right. Something disappeared. Hopefully it'll come back. All right. So we're back in high school now. What do? We're going to solve for x. And subtract 1 from both sides. And you can always do that with an equation or an inequality. And this is an inequality. So 2x is greater than or equal to negative 1. All right. And now what? Divide by 2. Now, you might remember that there's this glitch that happens when you're doing it. If you have an equation and you divide by something, as long as that thing you're dividing by is not 0, you're golden. Okay, you just do it. But if you have an inequality, which we have here, what's the rule? Do you remember? No?
If you take a negative, if you multiply by a negative, I know you have to flip the sign.
Okay, yeah. If you multiply by a positive number, the sign stays, the comparison sign stays the same. But if you multiply by a negative number,
negatives become positive and positives become negative.
yes. So if you multiply by a negative number, the sign actually reverses. So you reverse the sense of the inequality. Now, we're dividing by 2. Now, dividing by a number is really the same thing as multiplying by a number, because dividing by 2 is the same thing as multiplying by what? 1/2. Yeah, the inverse of 2. So 1/2 is positive or negative? Positive. Good. So we multiply both sides by half, and the inequality does not reverse. So that gives us, well, all right, I'll just add to it like that. I'm going to just do things in gory detail just for the moment. So that is, whoops, great. Okay. Oh, all right. That worked out fine. So that's how we got that. Okay. All right. So I do this explicitly now because you're going to be doing that explicitly for a lot more than I am. Okay, so the domain of G, the domain of the composition, all boils down to this. So it's well defined on X, provided X, if and only if means, the implication goes both ways. X is greater than or equal to negative 1/2. So the domain of F composed with G, wait for it, there it is. It's the interval from negative 1/2 up to positive infinity. That's a bracket. Where does that bracket come from? From here?
Roger is equal.
Yeah, the fact that this is greater than or equal to, which means x equals negative half is legitimate solution. So that's why the bracket's there, so we include the endpoint negative a half.
So basically, you just accepted that the domain of f was the range of g, and then said, okay, it can only be this much. So then you edited the domain of f based on the range of g.
Right. So if you're composing f with g, then you really you have to. Well, I mean, these points out here are never going to be outputs of g, so they're not going to be included. But these points over here are not in the domain of f, so they're not included either. So really, you get the intersection of these two, which is this little rounded rectangle thing there. That's what you have in the middle. Okay, and so this is the domain of the composition. And for every point x in the domain, f composed with g of x is f of g of x. Well, here I'm just going through and giving a general expression. So I'm not plugging in a value like -3 anymore. I'm just saying, okay, for all x such that this is true, here's how you get an expression for the composition. You just plug in the expression for g of x into here, and now apply f to it, which takes the square root of whatever it's given. All right. So that's an expression for the composition. All right. So we'll see lots of complicated. This is not really complicated. We'll see lots of expressions like this, where you have lots of operations going on. I've got a multiplication, I've got an addition, and I've got a square root. The thing about these expressions is very often, or all the time, these expressions are really just compositions of simple-looking functions, functions that have simple expressions, and you're just composing them one after another. So I'm composing, you can think of this as really the composition of 3 separate functions. First function just takes its input and multiplies it by 2. The middle function, the next function, takes its input and adds 1 to it. So if you apply the output of the first function to the second function, that actually gives you g, which is 2x plus 1. And then the final function, f, takes the square root of whatever is given it, and that's how you get the square root sign. Okay. So complicated expressions you can think of just as compositions of simple functions. Just you can compose any number of functions together into a chain. Okay. Composition is associative in the sense that you don't have to put parentheses. You just compose them into a chain. But the order of composition does make a difference. You can't switch the order around. For example, what if I compose G with F? You're going to get a different function there. Okay. So now this is first you feed X to F first. Okay. So F takes its input, outputs the square root of that. So I get the square root of X, and then I feed that to G. So where does that square root of X go?
The X position.
Into the X position in this expression. So I get 2 square roots of X plus 1. All right. So that's an expression for the composition. What is the domain? Okay, yeah, all the non-negatives, because X has to be in the domain of F. Okay, so X has to be non-negative. Great. So that makes the square root of X well-defined, and it's going to be real. Well, what does the square root have to be? Well, the square root of X has to be in the domain of G, but the domain of G is everything. So that's always going to be true. There's no restriction for number 2. But so the only restriction is number 1. And so the domain of the composition turns out to be the same, in this case, the same as the domain of F, which is the non-negatives, as you pointed out. Good. Let's try composing G with itself. No reason you can't do that. Okay, so what's G composed with G of X? Well, write it like that. So this is always going to be true. So this is just by definition. So now what? So I can substitute 2x plus 1 in for G into there, but now I feed that back into G again. And so this 2x plus 1 now gets substituted in for the x slot over here. So I get 2 times 2x plus 1 plus 1. Okay, so you heard the parentheses implicit in my voice. So you can get an expression like this, which you can simplify, in this case, pretty easily. So 4x plus 3. So that is an expression for the composite. What's the domain?
All real numbers.
All real numbers, right, because the domain of G is all the real numbers, and G will always give you back a real number, which is then in the domain of G. So, in fact, you can compose G with itself any number of times in the chain, and the domain will always be the entire real line. That's the domain. Great. All right. Let's see. Before I do this example, all right, I'm going to point out one thing that is actually not in the slides, but it's occasionally useful to know. So, just some basic concept here. Nothing really technical. So I said f of x is the square root of x. Okay. If you see something like that, okay, what this is really doing is it's defining a function which is called f. F, just the letter f itself, is the name for the function. And I'm telling you what that function is by telling you what it does to any arbitrary input x. But x here is what's known as a dummy variable. It's just a placeholder. It's just said whatever input you feed to f, well, let's call that input x. The output is the square root of x. There's no reason to use x here. Absolutely no reason. If I said f of y is equal to the square root of y, this defines the exact same function f. There's no difference. These two definitions are entirely equivalent. They define exactly the same function. All I've done is just change the name of this placeholding letter y. Here, the letter y stands for an arbitrary input to f. Here, the letter x stands for an arbitrary input to f. But the function defined by each equation is exactly the same. So f is the square root function. Without naming names of the inputs, it's the square root function. It takes the square root of whatever its input is. Okay. It's just convenient to assign a letter to describe the input, but it doesn't matter what letter we ascribe to it. So nothing significant about x here. We tend to overuse x a lot, okay, because it's the first thing you think of when you want to put in a variable. But there's no magic reason to use it. All right, let's go on. So another example, let's find two functions f and g. And when I say two functions, I really mean two simple functions, f and g. That when you compose them, given an arbitrary input x, you get this thing, which is x plus 1 quantity squared. So what's a natural, there's no unique solution to here. What's a natural example of an f and a g?
Squared.
Yeah, okay. So here what we're really trying to say is that f of g of x is 1 plus x quantity squared. Oh, it switched to 1 in the x. I don't know why I did that, but that's okay. It's the same thing. Yeah, so the thing is, you can think of you're doing two things to x. First you add 1, and then you square it. Well, here you're doing two things to x. You're applying g first, and then you apply f. So it's natural just to line up those things with the things you do in order. So g is the adding 1 function. It's the function that adds 1, and f is the squaring function. It's the thing that squares whatever its argument is. The argument is another word for input. Okay. So you can think of this process as a two-step process where you start with the input x, and then first thing you do is add 1 to it. So this is applying g. You always apply these things in right to left order. So when you take the composition of two things, you apply g first. It's the one closer to the input, which is on the right, traditionally how we write it. All right, so first we apply g, and we get x plus 1, and then we apply f, and that maps that thing to that thing squared. So this now is an expression, has to be an expression for g of x, if we think of it that way. So g of x is x plus 1. G itself, without mentioning x at all, g is the function which adds 1 to its input. F of x is, well, now I'm reusing x, so this is overloading x again. Maybe I should have called this y, so it's not confused with this x over here. But the point is, this x and that x are not the same x. This x, if you've done any programming, you probably know what a local variable is. This x is a local variable to this expression only in the box. Outside the box, x is undefined. The scope of x is entirely inside this box, this particular x. So the nice thing about local variables is you can give local variables the same name in different procedures, and they're completely independent of each other. So this x down here, defining f of x, has nothing to do with this x over here. All right. Well, f of x plus 1 is x plus 1 squared. So, without mentioning x, f takes some input and squares it, so that's really how f should be defined. Again, reusing our x here, but this x is local to this box, or this x is local to this box. That's sometimes a good reason not to use x. At least for people who are just trying to catch on first, I might have decided to call that thing y. So f of y is equal to y squared. Just so there's no confusion that this x has anything to do with that x. They don't. But that's how we do it. X is the most commonly used variable to define functions. So we tend to just overuse it. Questions? All right. All right. So let's find some compositions. So let's look at these two functions. So this is actually building to something. F composed with g and g composed with f. Here's f. F takes its input, multiplies by 3, and then subtracts 5. G takes its input, adds 5 first, and then divides by 3. Okay, so those are the two, f and g. Let's get an expression for the composition on some arbitrary input x. Well, we apply g first, and then f. So g of x is this thing, so we just plug that right in. And now to get f of this, what do? Take that inner expression and just substitute it in for that x, which is not the same x. Okay. So we get 3 times that thing minus 5. Simplify, what happens? Well, lots of stuff happens. The 3's cancel, right? And then the 5's cancel. Forget x. Okay. So f composed with g of x just gives you back x. The function that takes x and hands you back the same value x as output, takes input, so the output is equal to the input. That is sometimes called the identity function. So this is the identity function. It doesn't move any values. All right. Every value you give it as input, it gives you back the same output. That's called the identity function. It's called the identity function because if you compose it with any other function, it disappears. You just get the other function. So it acts like an identity under composition. Because it doesn't change the input. So whatever you feed the identity function first, the output's going to be the same, and then you just feed that to the other function. Or vice versa, if you compose the identity on the other side. Okay. So f composed with g turns out to be the identity function. Let's try g composed with f. Well, now I apply f first and then g. So f of x is 3x minus 5. There we go. Apply g to that. Now I'm taking 3x minus 5 and substituting it where? Am I getting colder? Yes, I'm getting colder. I'm getting warmer. Substitute it right up there. Okay, good. All right, 3x minus 5 plus 5. And again, lots of stuff cancels. First, the 5's cancel. And now the 3's cancel. Again, I'm going to also left x. So I get the identity function here as well. So I compose these things in either order to get the identity. Interesting. All right. Here's some other observations about f and g. So pairs of functions that do this have a special name. They're called inverses. If two functions compose in either order, you get the identity function in each case. Domain considerations aside for the moment, these are called inverses. So some more interesting observations about f and g. So if I apply f up to 0, I get negative 5, say. Okay, just plugging in some numbers here. G of negative 5, of course, has to equal 0 because when you apply both of these together, you're going to get back what you started with. F of 4 is 7. G of 7 is, well, let's just do that straight up. 7 plus 5 is 12, divided by 3 is 4. F of 5 is 15 minus 5, that's 10. And G of 10 is 10 plus 5 is 15, divided by 3 is 5. Okay. In general, f of some x is some output y if and only if g of that y is equal to x. And these are just 3 examples of that phenomenon. Okay. So this is the key fact about these functions and how these functions are related to each other. That this is true. Another way of looking at it is using the Venn diagram approach. F is mapping the circle on the left, its domain, into the circle on the right. So f of 0 goes to negative 5. G takes negative 5 and goes back to 0. In other words, G is undoing the action of f. F does something and G undoes it. It's like hitting the undo button. Okay. So G just gives you back the same thing. In general, x gets mapped to f of x, and G maps f of x back to x. So x is equal to G of f of x. And the thing about this diagram, it's symmetrical. You can think of starting on the right and applying G first, and then f. So here, you start with negative 5, you apply G, you get 0. Apply f to that, you get back negative 5. So f also undoes the action of G. F and G undo each other. So G of f of x is equal to x. And in general, if I start with y on the right, I get G of y on the left. Apply f to that, I get f of G of y, and that will equal y. So I also get this equation as well. these two equations along with this, these are equivalent. And this is the key property about these two functions here. Oops. These two functions satisfy these facts. All right, so they are inverses of each other when that happens. So another way to see what's going on, and this is good because this is our first example of graphing something. If we graph the function f, well, what do? F of 0 is -5, so we know how you graph f of x, y is equal to f of x. If you start with x equals 0, that is the origin on the horizontal axis, and the output -5 is 5 notches below the x-axis on the y-axis. So you have the point 0, -5. That point is in the graph of the function f, if you're graphing f. Now, if we want to graph g, so the point -5, 0 is in the graph of g. So the graph of g, here's the x value, -5, here's the y value. That point is over here. So here, x is -5, so you 5 notches to the left. And 0 notches up, so it's right on the x-axis. Okay, so the red point is in the graph of g, the black point is in the graph of f. Similarly for these other two, 4, 7, 7, 4, 5, 10, 10, 5. The difference here is that the coordinates are just swapped, okay, in each case. So for each black point, the red point, the coordinates are just swapped, and vice versa. So notice that these points, when you swap x and y, what you are doing is you are reflecting the points through this line, the diagonal line. This is the line y is equal to x. So these points are reflections of each other. Think of this as a mirror. These points are reflections of each other through this line. So the graphs of these two functions are symmetric with respect to this line, y equals x. All right, so I'm not sure I have this animated. But there is the graph of f. This is the black line, and let's see if the red marker works now. And there is the graph of g, sitting right there. And notice these whole lines themselves are reflections of each other in the axis. Okay. So the inverse of a function f it reverses the action of f. So each input is interchanged with the corresponding output. If f has an inverse, it's denoted by this. F to the -1 as a superscript. You can think of this as an exponent, if you like, but think of it just as a superscript, -1. So f of x is equal to y if and only if f inverse of y is equal to x. So f inverse now is taking the role of g right down here. So here g is equal to f inverse. But the inverse relationship is completely symmetric. So if g is the inverse of f, f is also the inverse of g. So we could also write f as equaling g to the -1. So this relationship is entirely reciprocal back and forth between f and g. So here are the fundamental facts. The graphs of these two functions are symmetric with this line y equals x. Assuming these are real valued functions, of course. F inverse is the only function that satisfies this. If you apply F inverse first and then F, you get back the original input x. And that's true for all x in the domain of F inverse. So if x is in the domain of F inverse, you can apply F inverse to it, and this will be in the domain of F. And you apply F and you get back x. If these are inverses of each other. And likewise, if you apply f first, and then apply f inverse, you'll get back x. And this is for all x in the domain of f. So if x is in the domain of f, you apply f of x. F of x will be in the domain of f inverse. So you can apply f inverse to that, and you'll get that. So there's only one function that does that. Given an f, there can only be one other function that does that. So that's why we call it the inverse rather than an inverse. The other thing is the domain and range of inverse functions swap. So the domain of f is the range of f inverse, and vice versa. The range of f is the domain of f inverse. Think of those two circles on the previous slide. One circle is the domain of f. The other circle is the domain of f inverse. This is also the range of f inverse, and that's the range of f. Okay, I'm doing this from your perspective. Okay, domain of f, range of f, domain of f inverse, range of f inverse. All right. Let's see. Is this a good time to take a break? Yes. Sorry. Take 10 minutes. 10-minute breaks last 10 minutes, so see you back in a minute.
I thought about planning every little bit. I didn't want to spoil their Thanksgiving weekend.
You want to spoil your Monday.
I'll ruin your Monday, but not your weekend. That's how I roll. I know I'm probably about 1 or 2 text messages away from a couple of people I can get. So. I would never do that. I enjoy it.
Guess I will pause this.
Okay.
Okay, we're back. So so we were just talking about inverse functions. So let's go back, get the brain back there. So for each function f below, let's try to guess its inverse function. Yeah, let's see. This has happened before. Yeah. I just have to touch the screen. Just bless it. All right. And so let's verify algebraically. So f of x is x plus 3. Very simple function. What do you think its inverse is? X minus 3, right? So this adds 3 to its argument. To undo that, you subtract 3. So f inverse applied to some input x is x minus 3. So let's verify that algebraically. Well, you can use one or the other of these two things. You don't have to use both. So let's use that one, say. And the left-hand side is, well, f inverse of x. You apply that first. That's x minus 3. Apply f to that. You get x plus 3. Got it. Now, you don't have to use both of these. You use whichever is convenient. But it's also, as long as you know that the domain and the range are swapped. Okay. So if the domain and range, if the range of one is the domain of the other and vice versa, then one of these is as good as both. So you verify one, and if the other is equivalent to it. All right. So that's true for this. Good. You get back x. So that's what we want. So f of x is 7x. What's the inverse? X over 7. Okay, so multiplying by 7 to undo that, you divide by 7. So let's verify again using the same equation. So plugging in x over 7, that's f inverse, that's what we think f inverse is. Plug that into f, the 7's cancel, and we get back x. Great. So nothing too taxing here. A little bit different here. 3x minus 5. What do you think the inverse is? Okay, yeah. So you got to undo two things here. There's a multiply by 3 and a minus 5. So let's look at this. Let's look at this a little bit more carefully, and you'll see that I heard some correct guesses out there, but we'll see why that's true. So the first thing you do with x is you multiply it by 3. So we can think of that as one function, just the simple multiply by 3 function, composed with the subtract 5 function. So, well, instead of giving this a letter, let's just call it times 3, and we'll call that subtract 5. So this expression is really the composition of two very simple functions. The times 3 function applied first. This is the important thing, the order. You apply the times 3 function first. Then you apply the subtract 5 function. Get 3x minus 5. To do the inverse, you start on this side and you have to undo things to get back to x. So to undo both of these, you undo them in reverse order. All right, so the last thing that was done is subtract 5. So the first thing you have to do is add 5 to undo that. That will give you back 3x. And then to undo the times 3, you do what? Divide by 3. Okay? So this is a general rule. The inverse of a composition is the composition of the inverses in reverse order. Okay. So if we start with some arbitrary input to the inverse, let's call it z, and now we can build an expression up for the inverse of f applied to z. Well, first thing you do is add 5, so you get z plus 5. And then you divide by 3, you get z plus 5 over 3. So the inverse of f is you apply the components of f. The composite, f is a composite of these two things. You apply the component functions in reverse order. You invert them in reverse order. And that gives you an expression for the inverse given an arbitrary input to the inverse, z. So just instead of using z, which is just a dummy variable, let's overuse our favorite variable x, and we'll say that f inverse of x is x plus 5 over 3. So first you do the plus 5, and then you divide by 3. That's the point. Okay. And I heard some people say that. Questions? All right. Okay, good. So we actually checked this before because this was our F and G example from the previous slide. So this was, okay. So here I'm now, the only thing is if you really want to assign letters to these, you could call this thing H and this thing Y, this thing G, this mapping G. So H is the multiply by 3 function, and G is the subtract 5 function. So the general rule, which I mentioned verbally, is that if you take the inverse of a composition, it's the composition of the inverses. So it's like you can take the -1 and distribute it across the composition. But when you do that, you reverse the order of the function. So to undo G composed with H, first you have to undo, well, here if you apply G composed with H to X, first you apply H and then you apply G. So to undo that, you have to undo G first and then undo H. So that's why the order changes. This example is a good example. All right. Good. Well, moving on. All right. So that should not have happened, but that's